Hi class, this is chapter 5 and we're going to be discussing radioactivity, otherwise known as radiation. We're going to be looking at different types of radiation such as alpha, beta, positron, and gamma radiation. So before we get started, I want to basically explain why I'm doing chapter 5 at the end. It's completely different chemistry than what we've covered, and I didn't want the class to get confused. So because the reactions we're going to be covering now are completely different, and I want to go over the differences in what we have studied to now something completely new. In chemical reactions, the reactions we've covered so far, we have starting materials, we have products, they balance, the atoms never change. If you have 4 on one side, you have 4 on the other, and so forth. So let's do a review of the chemical reactions. We understand them up to this point without chapter 5. We have a substance that's converted into another, but the atoms, the identity never change. So if you have 5 hydrogens on one side, you have 5 hydrogens on the other. Electrons are involved, so we either have ions or we have molecules, they share electrons. So there's either a transfer of electrons or they share them. But the nuclear particles, the nucleus, which involves the protons and the neutrons, do not take part. And even a lot of the electrons don't. We only consider the valence electrons when we're looking at bonding and breaking bonds. Reactions are accompanied by relatively small changes in energy and no change in mass. Well, up until this point, the law of conservation of mass means that if it's balanced on one side, it's also balanced on the other regarding the mass. So if you start out with 32 grams of whatever the starting materials, you must have 32 grams on the other. Even if you cannot see it, it may have been a gas that has disappeared. And, gases, unless you can detect them with your eyes. So for instance, like a fire, you have the wood burning, but a lot of the mass may have gone up in the air into our environment because it's a gas. Reaction rates, they are influenced by temperature, concentration, pressure, and catalysts. When I worked in the lab, some of my reactions, I would use heat because they would increase my yield and they would make the reaction faster. Now, nuclear reactions completely different. Atoms of one element are typically converted into atoms of another element. So yes, what I said was exactly what I said. You're going to start out with one element and you are going to end up with a completely different element. So that means even the atomic number is going to change. So what you start out on, let's say starting materials, the product is now an entirely different atom. Protons and neutrons and other particles are involved. We will be dealing with electrons, but not as much. This more involves protons and neutrons and not as much electrons. Reactions are accompanied by relatively large changes in energy and measurable changes in mass. This means that obviously nuclear bomb. These bombs have a very, 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 very small mass. But when they react, there's huge amounts of energy that goes off. Obviously, this is where if you have ever heard of nuclear bomb, this is what we're talking about. Huge amounts of energy. Where if we're dealing with chemical reactions and it's an exothermic reaction, the coffee mug might get hot. Big difference in energy. And reaction rates depend on the number of nuclei. So nucleus, which involves proton and neutrons. This is how there's a chain reaction and causes this huge energy buildup of a nuclear bomb. But they are not affected by temperature, catalyst, concentration, or pressure. So the things that have affected the normal reactions, I don't want to say normal, but the chemical reactions that we have learned about up to this point do not affect nuclear reactions. I hope that's understandable why I waited till the last chapter to cover this. So, radiation, natural radioactivity. Radiation comes from an unstable nuclei, so an unstable element. And chemistry is all about lower energy. The lowest energy of whatever we're looking at is the most stable, and everything wants to be stable. So in order for this unstable nuclei to become stable, it has to release this energy, these particles, in order to become stable. And that's what we're discussing, this energy that comes off in order for these unstable nuclei to become another element. And that radiation is in the form of alpha, beta, positrons, and gamma rays. So that's what we're going to be looking at. These are found, the unstable nuclei found in carbon, hydrogen, and elements with atomic numbers 20 and higher. Don't get really caught up on that because we're going to be looking at some and I'll cover them, and they're very weird names on most of the examples that I'm going to be looking at as this chapter progresses. So again, radiation, forms that we're going to look at: alpha, beta, positrons, and pure energy. So radioisotope is not any different in how it is presented. So remember what an isotope is. An isotope is, you have an element and you can have different isotopes of that element, and what makes that isotope different is the mass. The mass will tell you how many neutrons that isotope has, and they will all be different. The atomic number will never change, but the mass will, and that mass is going to indicate that it's a different isotope. So when we refer to these, we refer to them with the element name and the mass number, because the mass is going to indicate that it's different. So in this case, we have, for instance, iodine 131. And this is a radioisotope, where if you look on the periodic table, iodine 127 is not radioactive. It's the isotope that we would normally consider non-radioactive. So it includes the mass number in its name, and in this chapter it'll basically, there'll be something else to provide, so you don't have to guess which one's a radioisotope and which one's a regular. That's not what, I don't want to present anything that's confusing, so don't start worrying about that. You have to worry about which is which. When we discuss these, there's usually something that's given with it. It indicates it's a radioisotope, it states it, or it's talking about it's not stable, or alpha, beta, something will be given with it to let you know what you're dealing with. So again, when you look at this, we have the mass number, and you can easily look up the atomic number, whether it's an radioisotope or a normal, let's call normal non-radioisotope. The atomic number never doesn't change. They're the same element. One's just radioactive and the other one isn't. But the mass number is the indicator that you're dealing with something different. And in this chapter, there'll always be another indication that you're dealing with something that's radioactive. So here's a chart. You can kind of get some idea, examples of stable. So if you look up here, we have magnesium. This is a stable isotope. And then we have, so it's magnesium 24, iodine 127, which is exactly what I said. And this one is 131. And uranium has no stable isotope. And then we have radioactive isotopes. So we have magnesium 23. Remember, this numbers are the mass. We have magnesium 27, and which is different from the stable one. Iodine, we have 125 and 131. So iodine has two radioactive, so does magnesium, and uranium are all radioactive. Okay, so now let's get into the types of radiation. This may be extremely confusing and a lot of information in the beginning, but as we keep going through this chapter, it gets really repetitive. And so you're going to start, just by going through this, you're going to learn it without even trying to memorize it. It will just keep coming back to you. But in the beginning, I suggest I'm going to cover a chart. You guys might want to print that out or write it out so that you can easily refer back to it, because we're going to discuss a lot of protons and neutrons, and in the beginning it can be overwhelming to keep all of this straight. So the first one we're going to talk about is alpha. So I have to cut out on this. This is interesting to me because every time I see this, I have a childhood memory back growing up. I'm a 70s child, early 80s, and we always went shopping at a supermarket called Alpha Beta. And so every time I say that, that's all the memory that keeps coming up, is this grocery store that I went to. They have not been around since the 90s, which is probably where you guys, most of you probably were not even born yet. Okay, so let's start with alpha. Alpha particles are identical to a helium nucleus. So the symbol, we either use this as a symbol, but it's not just this, it's going to be with more information. So normally what I'm saying is that they tend to use this over this. And it's identical to a helium nucleus. So what does that mean? It means that it contains two protons. Remember, this is the atomic number. and the mass number is always listed on top. So the mass number comes from 2 protons and 2 neutrons. So somebody decided to make the alpha particle symbol as the helium symbol, and this tells you pretty much everything. An alpha particle consists of 2 protons and it has a mass of 4. And all of this is going to come into play when we start looking at actual reactions. So this is, again, when I get to the chart, I'll point out what you should probably keep handy to allow you to get this all straight. So an alpha particle has a mass of 4, and it consists of 2 protons and 2 neutrons. This matches exactly the helium element, so somebody decided to use that as the symbol for it. Then we get into beta particle, and a beta particle is a high energy electron. And remember, electron has a negative charge, so that's where you see the -1 here, and a 0 because an electron has no mass. So here we have an E to indicate electron. It's indicating it has a negative charge, which is -1, and no mass. So that's where the 0 comes from. And again, this is high energy electrons. The next thing is a positron. Now this one's a little confusing, so just kind of try to accept how I'm presenting it, because the book's not going into it in any more detail than what I'm about to say. So I hate to kind of say that, but unless you really want to tear into the radiation, this gets into physics and a whole bunch of other stuff, just kind of accept what I'm trying to tell you. A positron is similar to a beta particle. You can see it has an E, which means electron. However, this is considered antimatter, so it's because it's an antimatter, it's an opposite of an electron. So you have an E, but what would be opposite of an electron would be a positive one, so a +1 charge. So that's where this +1 charge comes from. But since we kind of still accept it as an electron, it has no mass, just like a regular electron has no mass, or the mass is so small we just kind of accept it as 0. So again, this is a positron. It's the opposite of electron, or a beta particle. So where a beta particle has a -1 charge and it uses an E as a symbol, positron uses a E as a symbol, but a +1 because it's antimatter, which means it's opposite of an electron. And then we get to the last one, which are gamma rays. And gamma rays are high energy radiation, and they have 0 charge and 0 mass, pure energy. And they are usually released from an unstable nucleus with some kind of other type of radiation, maybe alpha and beta along with it. So if you look here, a nucleus, remember these are unstable, they will release these particles to become stable, and in the process of doing that, for instance, with an alpha particle, it's also losing, that nucleus is losing 2 neutrons and 2 protons. So when it loses the protons, this is where it comes from, changing the element into something else, which is more stable. And there you go, 2 protons, 2 neutrons. A nucleus loses an electron, which is a -1 charge, but no mass. And then here I found a positron. So you see electron has a -E, it's a -1 charge. A positron is sort of like an electron. It's the opposite, but it's got a +1 charge. And I found this chart online. This is really pretty and nice. This is the one that your book gave me. Actually, this one is also very handy, but it's not as nice looking. But I found this one online. And see, remember the alpha particle, it will give it to you like this or like this. And it kind of breaks down exactly what all these mean. Beta particle is like this or like this. Your book tends to keep everything like this or like this. It really doesn't focus on either of these. So you should know them and understand when you see a beta. If you've taken enough math, you will understand that this is beta. But I have taken a lot of math and I've had to use this beta. And then it's a high energy electron. You can see it here. Positron looks like an electron, but a plus charge. Your book tends to use this more than this. Proton, when it says proton, hydrogen has 1 proton, so that's why it's using hydrogen, mass of 1 proton, or a P means the same thing. Your book's going to ask about some of this stuff, so this is why I want to put this out here, because your mind will go blank and go, well, I don't know what the symbol is for it. Yeah, you do. I'm giving them all to you. So when you read about this and it's asking, you will understand where this information, you can pull it from. A neutron has a mass of 1, but it does not have a proton with it. It's just a neutron. And then a gamma ray, pure energy, nothing else going on with it. If you get confused with that, this is the chart that I would ask you to handwrite, make a copy of, refer back to, because as we start going through problems, like I said, as we keep going through this, you're going to learn it. But in the beginning, it's kind of difficult to keep it all straight. And this is good because it tells you what the charge is to it. It tells you the mass. And as we start balancing, oh yes, we're going to deal with equations. You're going to need this information a lot. You're going to need to know how to do the symbol. And I told you, see, your book refers to it like this, not using the alpha. And all of these, this is how your book refers to everything. And then you're going to need to know the mass number, and you're going to need to know the charge number and which one goes with that. It's very important. Okay, so write the symbol for each of the following types. It's already started. So alpha, what is that? Remember, it is helium. So it's got a mass of 4, 2 protons, and it's a helium chemical formula. A positron, antimatter, opposite of electron. The word pos should tell you right there it's positive. So you do an E with a +1 and 0 above it because 0 mass. Beta is a fancy B. Just try to remember that. But in this case, I probably shouldn't have said that. Take it back. Because your book doesn't use that. It uses this. So again, an E, but a -1. So beta particle is a high energy electron. Okay, so now we're going to look at biological effects of radiation. Radiation is not something to be scared of, as we're going to cover later on. We are always around radiation. There's radiation in everything around us. A lot of nature gives off radiation in small amounts. And radiation is used to kill cancer. But we also need to know how much is good for us and how much is bad for us and how we can prevent bad things happening. So biological effects of radiation. We need to understand what radiation does to our bodies. So radiation is our bodies, the most sensitive cells are very sensitive to radiation. I don't think I said that right. But radiation affects our most sensitive cells. That sounds better. Which ones that undergo rapid division. So bone marrow, skin, reproductive organs, intestinal lining, cells, especially growing in children because children are young. They're constantly growing. Less sensitive cells tend to be our nerves, muscles, liver, and adult bones because we're already grown, so we're not forming anything new. Or cells that undergo little or no cellular division. Why does it affect cancer? Because cancer cells are rapidly dividing, so it's really sensitive to radiation, and large doses are used to destroy them. So we're going to go into, and it says it right here, different types of radiation penetrate the body to different depths, and we're going to take a look at that on the next slide, which is here. We're already at it. So you need to know the proper shielding when you're ever dealing with different types of radiation. First off, alpha particles, they are the largest particles that we are going to look at. They have the largest mass and charge. So because they're larger, they're not going to travel as far as the smaller particles of radiation. So if you look here, just paper or clothing and skin will protect against alpha particles. Unless you open your mouth or you ingest it internally, which then it could cause problems for you. But basically, your skin alone can block alpha particles because they don't travel very far. Beta particles. So we're looking at beta particles here. Beta particles have a very small mass, so they can move much faster and farther than alpha particles. They can travel several meters through the air, and we have a chart to this does not provide you all the information on the slide. There's a chart that's going to break down everything I'm saying here. It can pass through paper, and it can penetrate about 4 to 5 millimeters into the body. External exposure will bring burns to the skin, but it doesn't travel far enough to reach your internal organs. So here, lab coats and gloves are enough to help you. It doesn't tell me what type of gloves, but I'm guessing there's certain, it just says gloves. Gamma rays. Gamma rays are the most dangerous. You can see that passes right through this person's body. They travel the greatest distance because they are pure energy. So they have no mass, and they can pass through many materials, including body tissues. So they can do the most damage to your body. Extremely dangerous exposure. They're hazardous. Only dense shielding can block them, meaning lead and concrete. So how do you protect yourself? Well, you need to know first what type of radiation you would be dealing with. You need to know how much time, and there's, stuff all on this stuff. If you did my extra credit about the Radium Girls, they have studied a lot of this stuff. And unfortunately, because, there's been enough catastrophes that every time something happens, it's studied. So they understand it more and more. But obviously, increasing the distance from the source will help you to the further your way, the less exposure you have to it. I found this online. This is just kind of a visual. I'm a very visual person, so I like things like this. It shows you the alpha particles, and it shows you paper will stop here, aluminum will stop beta rays, thick lead will stop gamma rays and X-rays. Neutron rays, we're not going to discuss that. So that's why my X. But this is just more of a visual, so you can kind of see what I'm talking about, more than just that picture. Okay, so here's a chart of everything that I was talking about. This kind of covers the shielding, what source, what can give you, if you're looking at which radiation. Here's alpha, radium-226, beta, carbon, and gamma ray. Remember, alpha particles are not as dangerous because they don't travel as far. However, if you ingest it, that's a whole different ballgame. And if you looked at the YouTube video I put up for the Radium Girls, you will understand that they were doing the dipping and then they were putting it in their mouth. So they were taking in small amounts over and over again. That is what caused the problems for them. Okay, so indicate the type of radiation protection for each. I'm just going to put it up here. Heavy clothing, that will cover alpha and beta. Paper will cover alpha. Lead will cover all of the radiation that we've discussed. We're not discussing positrons right here, just alpha, beta, and gamma. And again, thick concrete will also cover alpha, beta, and gamma.